Ever wonder what happens when opposites attract in the world of semiconductors? Well, today we are talking about the p-n junction, the ultimate physics love story between electrons and holes. A p-n junction is formed when we bring together two types of semiconductor materials, p-type, which is rich in holes, and n-type, which has extra electrons. But it's not just any meeting. The crystal structure remains perfectly continuous across the junction, no cracks or spaces, just seamless atomic bonding. When this junction is formed, nature gets to work. Because of the difference in carrier concentrations, electrons start diffusing from the n side to the p side, and holes move from the p side to the n side. But wait, no one travels for free. As electrons and holes move, they recombine near the junction, leaving behind their parental origins, immobile ionized donors on the n side and ionized acceptors on the p side. This setup creates something magical, a region with no free charge carriers, known as the depletion region. And across this tiny but powerful region, a potential builds up. For silicon, it's about 0.7 volts, and for germanium, around 0.3 volts. This is called the built-in junction potential. Like a toll gate that stops further flow, this internal electric field keeps things in balance. Let's see exactly how this region forms next. Now let's zoom in on that defensive line inside the p-n junction, the depletion region, also funnily called the space charge zone. Sounds like a sci-fi battle zone, right? When electrons and holes diffuse across the junction, they leave behind exposed ions, positive on the n side and negative on the p side. These immobile charges can't move, but together they form an electric field, like a charged barrier that says, no more free passes. This electric field opposes further diffusion of charges. And when the flow of carriers due to diffusion is exactly balanced by the opposite flow due to this electric field, we say the junction has reached equilibrium. Now here's where it gets electric, literally. The built-in electric field points from the n side to the p side and creates a potential barrier. The strength of this field is given by E equals V naught divided by W, where E is the electric field in volts per meter, V naught is the built-in potential, and W is the width of the depletion region. W isn't fixed, it depends on how heavily either side is doped. More doping means more charge carriers but a smaller depletion width. Light doping gives us a thicker depletion zone. Isn't that neat? Now let's shake things up. What happens when we apply an external voltage across the junction? That's right, we talk about biasing the p-n junction. We begin with forward bias. Here, the positive terminal of a battery is connected to the p side and the negative to the n side. This reduces that stubborn potential barrier. With a lower wall to climb, electrons from the n side and holes from the p side gain the energy to move across the junction. Boom, current flows. But flip the battery and we enter the land of reverse bias. The barrier gets even stronger, like raising a drawbridge. Now only a tiny current flows due to the minority carriers, and it's barely detectable. Mathematically, the potential across the junction changes depending on bias. In forward bias, the new potential becomes V naught minus V applied. In reverse bias, it becomes V naught plus V applied. This asymmetry in response creates the nonlinear current-voltage relationship. So no, your diode doesn't linearly obey Ohm's law, it's got attitude. Time to unveil the star formula, the diode current equation. It's like the celebrity signature of a p-n junction, I equals I naught times open bracket e to the power qv by kt minus 1 close bracket. Let's unpack that. Current I depends on the applied voltage V. I naught is a tiny reverse saturation current, usually super small. Q is the electronic charge, K is Boltzmann's constant, and T is the temperature in Kelvin. Now for small voltage, you might not notice dramatic changes. But as we get past about 0.1 volts in forward bias, the exponential term e to the power qv by kt grows rapidly, and so does the current. It's like switching on a waterfall. But in reverse bias, that exponential becomes so small that I stays close to I0. The diode refuses to conduct unless the junction hits breakdown, which we are not diving into today. Alright, so what's the point of this electric drama if we can't use it? Lucky for us, the diode becomes a fantastic rectifier, the one-way valve for electric current. In half-wave rectification, the diode conducts only during one half of the alternating current cycle. Imagine clipping off the bottom half of a sine wave. The result? A pulsating direct current output. But we can do better. In full-wave rectification, whether through a center tap setup using two diodes or a bridge circuit with 4, the output remains positive during both halves of the cycle. We flip the negative half over like a pancake. The average DC output improves dramatically. For a full-wave rectifier, DC is equal to 2 times Vm divided by pi. That's double the efficiency of a half-wave version, where DC is only Vm over pi. But rectifiers aren't just about average voltage. We also check for ripple factor, how smooth the DC is, efficiency, how much AC we convert to DC, and PIV, peak inverse voltage, the maximum reverse voltage the diode must survive without damage. Let's put the physics to work in a real problem, calculating the depletion width for a given situation. Suppose the built-in potential, V0, is 0.7 volts. Let's say the acceptor concentration, Na, is 10 to the power 16 per cubic centimeter and the donor concentration, Nd, is 10 to the power 15 per cubic centimeter. The permittivity of the material is 11.7 times the permittivity of free space represented by epsilon naught. Now, the depletion width W is given by this equation. W equals square root of open bracket 2 times epsilon times V0 divided by Q, close bracket, multiplied by open bracket 1 over Na plus 1 over Nd close bracket. When we plug in all the values using C units, we get W approximately equal to 2.1 micrometers. This example shows something quite important. The depletion width is wider in lightly doped junctions, especially on the side with lower doping. So design really matters. Let's quickly lace up what we've just learned. We explored the key diode current equation, I equals I0 times open bracket exponential of QV over KT minus 1 close bracket. We saw how depletion width W depends on doping levels through the formula. W equals square root of open bracket to epsilon V0 over Q, multiplied by open bracket 1 over Na plus 1 over Nd close bracket. And for rectifiers, the average output for a full wave setup is 2 times Vm divided by pi, while for a half wave it's Vm divided by pi. At equilibrium, the PN junction holds its ground with a depletion region where diffusion and electric field drift balance each other. When we apply a bias, magic happens. The diode conducts or blocks based on the potential barriers change. That's how we get rectification, turning AC into DC. And finally, thanks to its exponential IV behavior, a diode acts like a smart gatekeeper, highly conductive in one direction, super resistive in the other. That's why it's a hero in power circuits all around us. That's it for today's concept. Remember, in the world of electronics, the PN junction is a tiny gate with mighty consequences. Physics lets us peek behind the curtain. Until next time, keep the current flowing and the curiosity glowing. See you in the next session.